Hi, this is Allison Rose, and this is my problem presentation for Math 626. The problem I've developed is, the audience is for high school sophomores and freshmen taking geometry. And the question is for them to develop a method for calculating the area of any trapezoid. The students will not have been introduced to trapezoids prior to this. They will, however, know how to calculate the area of a triangle and the area of a parallelogram. They have not been exposed to any formulas for finding areas of trapezoids, kites, or regular polygons at this point. So this would be considered a problem for this audience. My group did define a problem as follows. A problem is a task that needs to be completed where the solution may not be obvious. So at this point, because they haven't they haven't calculated the area of a trapezoid before, their prior knowledge can help them get to the area, but it's not going to be an obvious solution to them. So this would be an adequate problem for sophomores in high school. Step 1 is to understand the problem. Again, our problem is to find the area of a trapezoid. So first we have to investigate some vocabulary. What is a trapezoid? What does it look like? What are its characteristics? Well, a basic isosceles trapezoid looks like the figure on the left. Now, the bases are defined to be the pair of parallel sides. So what I'm going to do is I'm going to label the bases. Since this is a smaller base, I'm going to label this with a lowercase b. This is defined to be a base, and this other parallel side here, I will label those with parallel symbols. This is our larger base, so I'm going to call that a capital B for big base. So again, those are the parallel sides are defined to be the bases. Now the height is defined to be the distance between the parallel sides, and we always measure distance between two parallels to be the perpendicular distance. So this is going to be our height of our trapezoid. And then we've got the non-parallel sides. These are called legs, and I'm going to call this leg number 1 and leg number 2. Okay. So what kinds of trapezoids are there? Now, typically in my lesson at the high school, I would not discuss this obtuse scalene trapezoid. However, I am going to include it for this presentation. We have 4 different types of trapezoids. The first is our isosceles trapezoid, and just like a isosceles triangle, this means the 2 legs are congruent. We get a lot of properties from that, but that's the definition. This is one type of trapezoid. So again, we are investigating. This is step 1. We are understanding what a trapezoid is right now and all of the different kinds of trapezoids. So an acute scalene trapezoid, this means that the base angles are acute on the larger base. So this angle right here and this angle right here are acute angles. They are not necessarily congruent, but they are acute. And scalene meaning that these 2 legs are not the same length. They are different. An obtuse scalene means we do have one obtuse angle on this base. So this is an obtuse angle, and this is an acute angle. So that's where the name obtuse comes from. Acute, both are acute. Obtuse, one of them is obtuse. And a right trapezoid. A right trapezoid has 2 right angles, and the 2 right angles cannot be on the same base. They must be between the 2 bases on one leg. Okay? Now, what measures are available for finding the area? Well, we could find anything we really need on this trapezoid here. We can count out the small base, because all of the trapezoids we will be working with are going to be on grid paper. So we could count the small base, we could count the larger of the 2 bases, we could count the height, And these slanted, the legs here, those are not countable. Most of the time they're not countable unless they're vertical. But we could use our Pythagorean theorem, and you have seen that before. So that might be another tool in our toolbox, along with our distance formula, which you have also used prior. Now we're going to continue trying to understand the problem that we have at hand, and we are going to attempt to actually find the area of a trapezoid. Now, the first question I would pose to my students is, can we turn this problem into something simpler? Can we figure out how to simplify this so that we can maybe figure out a strategy for solving this thing? Now, to make it simpler, what I mean by that is, can we turn this into something we know how to find the area of? Now, we know how to find the area of a triangle. We know how to find the area of a rectangle, a parallelogram. So a lot of my students, their gut instinct is to draw this. A trapezoid with the two triangular sides cut off, and you can find the area of all three figures and add them up. And so this is the figure that most of my students run to at first. I do an activity similar to this in my classroom, and I do rather enjoy this particular activity. So now the question becomes, can we find more ways to alter this problem so that it's simpler? Can we find more ways to maybe cut apart this trapezoid so that we can actually find the area? Our goal is to find the simplest way to break this thing apart into familiar shapes so that we can calculate its area. So this is one way in which we could do this. Now, another way we could break apart and reconfigure this trapezoid would be by taking this triangle on the right-hand side, eliminating it, and rotating it and putting it over here. So we could do this, and then that would result in a rectangle. Now, this is only if these two legs are the same, because this hypotenuse has to match up. So that's a key point there. We could also split this trapezoid into two triangles, since we know how to find the area of a triangle, and we know how tall this trapezoid is. The height of our trapezoid is also the height of our triangle. So we could do 1/2 times base times height for this triangle and 1/2 times base times height for this triangle as well. Find the area and add them up. Another one that my students often come up with is turn this into a parallelogram and subtract the extra area. Because again, we know how to find the area of a parallelogram, and we know how to find the area of a triangle. Oops, wrong slide. There we go. So now that we are familiar with our problem, we understand where we're going to go, or what a trapezoid is. We know how we can use the tools that we know. Now we're going to develop a plan for how are we going to tackle this, calculating the area. So what we're going to do is we're going to choose a strategy to use. And we're going to find the area of several examples, and we're going to use this one strategy to find the area of all of our examples, as many trapezoids as possible. That way we know if our strategy is going to work always, if we try it out on all of our different types of trapezoids. And we're going to, of course, use what we know about the area of triangles and parallelograms. Second, we are going to look for a pattern in what we find and see if we can generalize this so that we can possibly use it with any trapezoid whatsoever. So what are the strategies we were able to develop? Are the same variables used consistently for various problems? So are we using the same the numbers from the same places on our trapezoid consistently? So maybe we could generalize and come up with a formula at a later point. Are the calculations similar for the area of each trapezoid? And can one strategy be used for all different trapezoids? So these are the things that we're kind of looking for here. The first step, we're going to go through those to choose one strategy and use it to find the area of several different trapezoids. In fact, all of the different types of trapezoids that we discussed up here. Okay, so step 3, we are going to carry out our plan. We are going to go through the area of isosceles trapezoids and the other 3 types of trapezoids as well. And the first strategy I chose, or the only strategy, now keep in mind this, we're just carrying out the plan right now. I'll talk more about a second strategy later. But we are just going to find the area using one strategy consistently on all of the different kinds of trapezoids. So I've drawn in here several different trapezoids, and so the first thing I would have my students do is to document the measurements that they think are important for the figure. And so when we are calculating the area of a triangle, we need the base of our triangle and the height of our triangle. Now, the height of our triangle is this measurement right here, which is the same as the height of our trapezoid. So I'm going to be recording the small base, the height, and this longer base, because I'll do half times base times height for this triangle as well. So I have done this already for all of my trapezoids that we will be calculating the area of. And so I would give my students many different trapezoids to make sure that they understand their process and understand how it's going to work here. And then we work out the areas by finding the area of the left triangle and the right triangle and adding them up. So you can see here we have base times height divided by 2 plus base times height divided by 2. The area of this one here is 32. And so on and so forth. And we go through another example and we're able to find the area of both triangles, because that's what they know right now, is how to find the area of a triangle. Left triangle plus right triangle is equal to the total area. Now, what if we are talking about a right trapezoid? So we've got 2 right angles here. What if that's the case? Well, we can still break it down into 2 triangles. And so you see, our formula doesn't really change. We can still use that same strategy that we were using before. What if it's a different kind of trapezoid? What if it's an acute scalene trapezoid? So it's just not isosceles and it's also not a right trapezoid. Again, same thing happens. We have our 1/2 base times height, 1/2 base times height. We add them together. We get our total area. Now, what if it's an obtuse scalene? Now, this is the one, like I said, I don't typically cover this type of trapezoid in my lesson. This is a trapezoid with one obtuse angle and one acute angle on the base. And so it actually turns out to be the same way of calculating as the others. 1/2 base times height twice, once for each of the triangles, and you add them up and you're done. Now, we have found a method that is successful in calculating the areas. Now, our last task here is to look for a pattern, and we're still carrying out our plan. What strategy were we able to develop? Well, we cut our trapezoid in half into 2 triangles. So our 2 triangle strategy was a success. We were able to find the area of all the trapezoids that we set up. And we considered all of the different types of trapezoids, so that was good. Are the same variables used consistently for various problems? Yes, we were consistently using the 2 bases and the height of the trapezoid. So this is something that is important to consider, especially if we do an extension and ask for a formula. Are the calculations similar for the area of each trapezoid? So yeah, we were doing the same thing over and over and over again. And can one strategy be used for all types of trapezoids? Yes, we were able to use that on every type of trapezoid. Now, we have carried out our plan. We went through all the different types of trapezoids. We carried out and looked for patterns. Now we need to look back and ask ourselves, are we really correct? could we have used a different strategy to come up with the same result?